Good morning. So we are continuing our discussion on integrated injection logic that is being continued. In the last class, though it was not a video lecture, but I just discussed informally some of the salient points which I should mention once again because all of you are not present yesterday. I told you that because these transistors in I2L, these are so-called vertical transistors which are responsible for the switching operation as indicated. All these transistors are vertical NPN transistors as compared to these ones. These are PNP transistors, lateral. You remember that these vertical NPN transistors, they are the collector and emitter are just the opposite of that which is used in conventional devices. As you know that in conventional transistors, the top N plus regions are emitters, whereas the bottom, either the N plus buried layer or the substrate is the collector. But in this case, the whole N plus substrate is emitter, whereas all these N plus regions in a P-type base are collectors. As a result, as you understand that these transistors work in an inverse mode of operation. They do not work in forward mode. And as a result, the beta of the transistors is much less. In the forward mode, when this is emitter, this is base, and this is collector, because the NP junction, N plus P junction has got a very high injection efficiency, the beta or alpha is very large for the forward mode. Whereas in the reverse mode, the beta is usually quite less. It varies from 5 to 15 maximum. It is very difficult to achieve a beta value in the down, which I call beta up. I call one is beta down means forward mode or beta F. The other is beta N, forward, and beta R, reverse mode. Or sometimes we call it beta up and beta down. Beta up may be 100, 200, just like conventional transistors. Whereas beta down, it is very difficult to achieve even 15. So this is a problem because when you want to want to achieve a very high gain, and which is very important for getting high speed, high gain bandwidth product, as well as a very good shape factor, a very good noise margin. And in that case, you know that this low gain, low current gain will matter. And that is I pointed out that is one of the drawbacks of I2L, that it may not offer you a very good noise margin unless you be very careful, as well as speed intrinsically is less. Another thing I also mentioned, but because the emitter is a very wide area now compared to the collectors, collector areas are very small, whereas emitter area is very large in this particular case. So when the emitter is forward biased during this saturation region, when emitter as well as collector both are forward biased, but emitter area being very large, forward biasing means a lot of carriers are injected into the entire region, which comprises not only intrinsic base but also the remaining base, which is called extrinsic base. And these extra carriers which are injected in the extrinsic base, they take a lot of time to be lost totally, so that the storage effect is much more pronounced in I2L transistors compared to conventional transistors. Because it is remember that I2L is a very heavy, it is a saturation logic. It is not only a saturation logic, the transistors are saturated very heavily during when they are turned on. So this is one of the, these are the important things to be kept in mind in connection with I2L. The transistors, the basic vertical NPN transistors, they are operated in the reverse mode or inverse mode, and as a result, the gain is less, the storage effect is more. Another thing is that these lateral PNP transistors, which otherwise should have been, that I just showed the original one, is like this actually. Each injector is like this only. There is an inbuilt lateral PNP transistor, but they have been so trickily simulated by a common injector level in I2L, which I discussed very clearly. But you see that these lateral PNP transistors, in order that they serve as a good current source, they should also have a good, a reasonably good gain. But unfortunately, it is a lateral PNP transistors. The base width cannot be as small as that in a vertical transistor. Vertical transistor, this base width can be controlled precisely, and it is usually less than a micron. Whereas in the lateral transistor, the effective base width, it is very difficult to make very small because everything is controlled by MOS geometry. So there is a limited, it is found, and most of the carriers, suppose this is the P NP lateral transistor, okay? When this junction is forward biased, okay? When this junction is forward biased, the holes which are injected, they are injected in all directions. Only those who are injected near this so-called P region, which is the collector of the PNP transistor, this P is the collector of the PNP transistor. Only those holes reach. As a result, you see that injection efficiency of such a junction is very small. So the lateral PNP transistor is also another drawback with them is they also offer a very low beta. It is rather difficult to have a lateral transistor of gain more than 5. It is difficult. Up to 5 is not difficult, but above 5, again, there are design difficulties. Of course, the technology today is much superb. You can create this region very narrow, and some other techniques which have been incorporated by which even lateral transistor gain can be reduced to 50. This is very superior technology of today. Otherwise, lateral transistors offer a very, this is again a small drawback for the I square. This thing should be kept in mind. So this is one thing. Second thing, I was discussing in the last class the various realization techniques for the I square L. One is the I square L NOR is most simple, simply wire the outputs. And if you need in various functions to be generated out of the variables say A, B, C, then I make use of the multiple collectors as indicated, which I discussed in the last class. Okay, this was very clearly discussed, and you see that there is a natural advantage in I square L. Use of multiple collectors here really does not increase the transistor count. So each collector is effectively behaving as an independent transistor with, of course, a common emitter and common base. Suppose I had not this facility, I would have used separate transistors in separate blocks and make the same. So this is a great advantage in I square L, which helps in achieving very high packing density. Then I discussed I square L NAND. In I square L NAND, I say that you just wire the input and you get the NAND function generated at the output. But again, if you want to have different kind of functions generated out of ABC, then we have to use another set of transistors at the input. And not only that, you have to apply the complements of the variables and not the exact variables. Okay, so this is, you can say that therefore conclude that I square L is not a natural gate of I square L. Let us consider today the I square L OR. I was quickly discussing all the gates, basic gates. In this case, OR means you can conceive as NOR and invert, or otherwise. Let us discuss that. If I forget to draw these current sources everywhere, please do it yourself. This is very important. So what I have done, I have just made, by wiring the output, I have made a NOR function, and then I have passed it through an inverter to produce the OR function. It can be viewed both ways. That is, I can draw a block like this. Or I can also draw a block like this. This block shows an OR function, a NOR gate at the output, and which is inverted to produce the OR gate. Whereas this block shows an AND gate. You just see that this block shows an AND gate because we have wired the input. Only thing is you have applied the complement of. So simple thing is, if you want to create a OR function, OR gate, you invert the inputs and then wire them and pass it through an inverter. Alternatively, you can think otherwise, you produce a NOR gate and then invert. So it is like this. And if you want to produce multiple functions, as in previous case, again you have to make use of this multi-collector transistors. So this is a sampling. Suppose I want to produce this one. And so on and so forth. So again, you see that the I square L OR also there is a natural advantage in it. So you know that by going from OR to for the multifunction, multivariable input case, you see that you really do not have to, the transistor count does not increase that way. So there is a natural advantage in it. But definitely compared to NOR gate, as indicated earlier, which is most natural, you see the number of transistors is minimum here. You just see only with 3 transistors, you can generate all these functions possible out of the combination of A, B, C. Just by using 3 transistors, you get the NOR gates very effectively without any difficulty. And you don't have to apply any complements at the input. On the other hand, for the NAND gate or OR gate, they are very similar. They are very similar in the sense. It is very similar. In this case, only thing is you have to apply complements at the input for NAND, and for a OR gate, simply you have to apply the same variables, not the exact complements. So basically, the same transistor count-wise, they are identical. Similarly, for the AND gates, you can visualize in different ways. Alternative approach is you just first NAND it and then invert. So this is there are 2 alternative approaches. One is this one, the other is this one. So if the complements are easily available, this one is better because there is automatic isolation. Because I want to generate that, you can easily check now. Suppose you want to produce functions like this. You have to produce functions, multiple functions out of A, B, and C variable as before. So you make use of, as before, a number of transistors, same as the number of input variables, same as number of input variables. Please remember, that is an important thing. See? And then naturally you are producing the inverse functions, the complements here, as like this. Then you have to pass it through. Suppose I want to have produce A and B and C. What do you have to do? I have to take 3 transistors as before. So normally we draw it simplistically like this. This is 1 transistor, this is 1 transistor, this is 1 transistor. You short the outputs. Only thing is you have to apply this one here, this one here, and this one here. Please remember at each node there is a this thing that must not be forgotten. And here you produce A, B, C, and that way you can produce B, C, or A, B, whatever you like. Suppose I produce A and C. So what I do, I take another 2 transistors, so and you produce this one using this approach, but I could also use the other approach also, but then we need further isolation, another isolation at the back. And if you have, this is a standard technique for AND gate realization. Complement the variables, where them, and where the outputs. Similarly, you can generate all the other functions, whatever you like. And if I have gone through all these things, then I can write down the certain rules for creating the different functions. So to implement do the following. One is NOR. What do you do? Where the outputs. This is 1. 2 is very similar, that is AND or NOR are very similar. So what we have to do, where the outputs, but complement the inputs. That is very important. Apply complements of inputs. Then 3 is NAND gate, where the inputs. And 4 is the corresponding OR gate. If very similarity is there, where the inputs complemented. Where the complemented inputs. Simply that means you just pass it through inverters, all whatever this thing, but here that's the advantage. Let me repeat once again. This is for the OR. It is not necessary to have complemented inputs, because you have to, naturally for isolation purpose, you need multi-collector transistors. Therefore, automatic complementation is done here, automatically. But in the other example, for NAND, you just see, for doing the same thing, you have to apply complements. Same thing, these two circuits is exactly similar, exactly similar. Only things here you are directly apply ABC, and here, but I mentioned earlier that normally in a overall, if you just think the whole chip, the variables and their complements are available because they are produced even at the input side. So you don't have to really worry about whether the variables or their complements which have to be applied. So that's not a major concern. So this is the more or less in nutshell the the methodologies to produce the different basic logic gates using the I square L concept. Let us now see some examples. I'll just show you initial first example for a half adder, how to realize a half adder circuit using I square L. A half adder case, the sum, which is usually we write as is nothing but exclusive OR, can be expressed, as you remember, if I want to utilize them using the NOR gates, then I can write it as this. You can easily prove it yourself, there is nothing in it. And to remember, carry is simply AB. So in the case of half adder, which is where sum is nothing but the exclusive OR of combination of A and B, you can write it like this for my convenience here. We shall see, because it is the easiest. If we could use NOR gate, it is the most convenient in I square. And therefore, I have written it like this. I have just re-expressed it like this. Whereas AB is very simple. You can use the complements of inputs and just pass it through a NOR gate to produce. So let us now see. Basically, therefore, your circuit is like this. You are producing first A and B here. We are applying A and B here, so that here you get A, B NOR at this point. Then I need AB, so I have to first invert them, pass it through a NOT, and I have to invert it, passing through a inverter or NOT. Then again it has to go through this thing to produce AB here. Okay? And ultimately, this one is giving straight use C, the carry out, the carry, or carry out you can say, carry out from the half adder, and same thing you apply here, and passing through an exclusive OR gate, you get S. So I will follow this technique of realization of half adder using I square L, because it is convenient for me. I have used mostly NOR gates, excepting for these inverters, which could be easily implemented using I square L. Inverter is nothing, just take output from one collector, you get the inverter. So inverter is nothing. Similarly, NOR gates are very simple. So I will utilize this particular logic schematic to realize I square L. So let me do it. You just try it yourself. So I just take, as before, because there are two inputs, two transistors. At the input of which I will apply my A and B. Okay? Then simply where the outputs to produce first the OR, the NOR function. So here automatically your A is produced. Then take this, then I have to produce this one. First the inversion, I have produced this one here at this point, very simple. Then I have to invert and then pass it through a NOR gate. So invert means simply you take output from here, you will get the inverted things. These are the inverted things. Okay? And So you are really applying A bar here. Similarly, you take another transistor and take this one to the input of this. You are producing B bar here. Wire them, and you will get, what you will get here if you just wire them? You get AB. You get AB produced. Just wire them, and you are getting AB at this point. Then I have to make this AB and A plus, this one and this one again have to pass through a this thing. So what I will be doing? I will be simply taking another transistor here and another transistor here. This one will be coming from here. These two are joined together. Ultimately here you get your S from this point, carry. So the transistor count is 1, 2, 3, 4, 5, 6. What is the effective number of transistors? 8, because 2 collectors have been utilized there. Effective number of transistors, if you did not have this concept, then I had to use minimum 8 transistors. But now I have been able to manage it using only 6 transistors. Now how to realize it in the actual I2L? How to realize? Actually, I have shown. Please see that these PNP transistors are all distributed. These PNP transistors are all distributed, which are not indicated in the diagram. I will find afterward, if you just go through any papers, a Journal of Solid-State Circuit, recent papers tonight, or even 10, 15 years ago paper, you will find that for simplifying the circuit diagram in I2L, even they do not show the ground. The emitters are just shown like this, just floating. And here also they do not show the injector. This injector, what is this? What is the symbol for this? Is a constant current which is supplied by the injector. What is the significance of these lines? Some supply. Maybe it should be a constant current supply and not a voltage supply. Please remember, that means you have to take a voltage source, and in series with that you have to put a resistor. Then only you don't connect directly a VCC kind of thing here. You must feed a constant current, and that whatever you generate, whatever way. Normally constant current, instead of bothering that, what we do, we take a power supply and pass it through a series resistance. We control that resistance to adjust the current. That's the usual technique. But if I do not want, I want a constant current really to be supplied all through, independent of time, independent of voltage, temperature, etc. Then naturally I have to design a constant current source of the particular value, then and connect it to the injector, whatever injector I have shown in the main diagram. That's the thing. But please remember, so when we consider a big I2L circuit, firstly we do not show the ground, but please remember the ground line has to be distributed. Is it necessary to distribute the ground line or not? Is first generation I2L, which I have discussed in the last, first generation means usually the N plus, you just take an N plus substrate. In that case, is it necessary to have to make a metallization on the top to have a ground line? Because N plus itself, so you don't have to worry about the ground. But what about these sources? They are distributed. So you have to provide that injector current, and that also you have seen how easily it can be done. Just place an injector rail, and on either side you place the bases. The problem is solved. Therefore, all these things really do not occupy much space. Though effectively there are a large number of transistors, all these PNP transistors, whatever have been shown here, they are achieved through very simplistic, very tricky way of realizing them using a MOS transistor concept. So let us now see that how this thing can be realized on the chip. What may be the probable layout for this particular thing. you can try yourself. So what I'll be doing here, as before, I will just draw a injector. Which is a P plus injector as before. This is an injector. And there are 6 transistors in this diagram. Let me call them like this: T1, T2, T3, T4, T5, T6. T5 and T6. Exactly, I'll be now. So I'll be requiring such transistors here. All the transistors, the T1, T2, and this T1, T2, I think I have not followed that. Let me check. T1, T2 is the input ones. Yeah, okay. So what I'll be doing, I'll first put this transistor here. With 2 collectors. This is my T1 and this is my T2. Okay? And at the input, you are connecting your A and B, please remember. Now, one of these collectors are connected to form that A plus B or NOR. So I'll just connect them and transfer to the base. So what I'll put the third transistor T3 here. This is my T3, this transistor. So this transistor is this one. You see, at the base of which I am applying this wired outputs of A and B. So T1 and T2, the one of the collectors have been shorted. Each collector of the 2 transistors have been shorted, and they have passed over to the base of the next transistor T3. Okay. Then these are the other collector supply the input to T5 and T6. The other 2 collectors of A and this T1 and T2, they supply inputs to T5 and T6. So what I have to do is I have to place the 2 other transistors called T5 and T6 on the other side. These are this T5 and T6, these 2 transistors. I have applied A bar here and B bar here. So A bar has been connected to the base and B bar has been connected to the base of this. And this to be wired to produce the C function, the carry out. So and that thing will go to the other base, the base of T4. The wired output of T5 and T6 has to go to the input of T5, T4, and T4 therefore I will place just above it. Only thing is the relative locations of the base and collector, that you carefully see. And this T5, this is called T4. You just see that T4 and T3 output is wired. Output is wired. So these two outputs are wired. And you get some here. You compare your circuit, whichever drawn in your notebook, along with this diagram. You'll find that I have placed the different transistors. You see there are only two transistors with multiple collectors in this particular case. That is transistor T1 and T2. Other transistors are single collector transistors. That T1 and T2 I have placed just at the bottom left of the injector rail. And these are the bases. I told you in the very beginning that you can interchange the positions of the base and collectors, and that's the beauty of I2L. You have seen that here, for the convenience of routing, I have placed the two bases of T1 and T2 at the left. You see that, however, I think you know that this, whenever I draw, that's the convention, whenever I draw a box and put a cross here, it indicates what is it? Contact holes. This indicates the contact holes which are used for making the contacts with the different emitter, base, collector, etc. So this is the base contact hole. This is P+ injector in an N+ epitaxial film. If you remember the diagram, this main film is the semiconductor wafer substrate is N+, on which there is an N-type epitaxial film, and then we have a P+ diffuse region, which is quite wide, maybe quite strong, because it has to supply a lot of current to the different transistors. Okay? And on either side of it, you have placed the different bases. Each base is usually lighted up P regions. Please remember, these are all P-type regions. All P-type regions. And the big blocks, the squares which I have indicated here, these are nothing but emitter diffusion. In this case, emitter or collector diffusions. And at the center, again, it has been not shown properly. Actually, I have drawn each thing. It is something like this. Each collector, actually, I wanted to draw them like this. This is nothing but the contact hole of the collector. So this one and this one is the same. And this is the N+ diffusion of the collector. So each block is N+. Each block is N+. Please remember this. So what I have done is that by convenience, I have used these two bases as the inputs. Then simply I have taken one collector each, shorted them, and applied to the input of T3 according to my layout. So I have just vertically, you see that now in this transistor, I have placed the base exactly above the two collectors. This base exactly above the two collectors. And these two collectors, which give you the A bar and B bar, the complement of the two variables. So you just straightforward connect them to the two transistors T5 and T6, their bases. Now you see that the bases are close to the injector, just opposite. These two transistors and these two transistors, they are opposite in nature, but it works nicely. There is no problem in I2L. So you now straightforward collect it like this. Then the outputs are wired and is connected to the base of the T4, is connected to the, now this base is in the right hand side for my convenience. And then ultimately these two collectors intentionally have been kept face to face so that they can be shorted and you get this. Why I have done all these things? To avoid crossovers. to avoid crossovers of metal line. These are all metal links. Actual practice, we have to put a metallization and all these things, which I have not shown. I have simply shown the metal links. I could have shown in different colors. These indicate the metal link between the different things. That's how our aim is finally to, whenever you design a chip, to implement a chip, our aim is to see that these transistors are arranged more or less in a square fashion. Ultimately, you see that I have tried to make the whole thing more or less in a region which is at least close to a square. This is called square aspect ratio. The chip is not usually a thin rectangle. It is usually a square, or sometimes a little bit. X and Y may be a little bit different, but not much. So I have to place the transistors in such a way while doing the layout that overall aspect is almost a square. Another thing you have seen, that this distance has been kept the same. This width of the base have been kept for the same for all the transistors. Similarly, the separation between the injector and the bases, they have also been kept the same. What does it signify? The width of each base and the separation. So they supply the same I injector to all the bases. Total, what is the total current supplied? Is another 6 times. 6 times I injector. The actual total injector current is a 6 times I injector individually supplied to individual transistors. Has to be remembered. So with this, I think today time is over. I will request you to do in the same way you design. Firstly, you realize the logic realization of a full adder circuit and its chip realization. Logic, this is for half adder, but logic realization of a full adder and its chip implementation, that is layout implementation. Again, you try the same procedure, try to realize everything using as far as possible using NOR gates and inverters. Try to. Okay? So this is, I'm just giving you the problem for the next